Well, hello everyone. Thank you for joining me today. My name is Chi, and I'm an apps engineer from the Comparators team here in Santa Clara. And today we're going to take a slightly technical overlook at the comparator. Feel free to stop me and ask me any questions throughout the presentation. And I will also be sending out this PowerPoint to everyone as well as some links to our tools that I will be discussing today. And today we're going to discuss the basic functionality of the comparator and look at the two main types of comparators as well as some of the key DC and AC specifications. We'll also take a look at the effect of noise on comparators and how we could add hysteresis to alleviate that effect. And we'll also talk about startup behavior, and I'll also show you guys how to find our parts and select them using some of our tools. And so let's begin by introducing the basic functionality of a comparator. And similar to a standard op-amp, a comparator has two inputs, one output, and two power supply pins. And from a schematic perspective, it looks quite the same as an op-amp, but its intended function is quite different. And the comparator gets its name because it compares the two voltages applied at its inputs, and it sets the output voltage based on that input level. And one input is usually considered to be the primary input signal, or Vin, and the other input is considered to be the reference signal, Vref. And these inputs may have AC and DC components. And the output voltage, Vout, can be set to one of two levels, a high level or a logic high, and a low level or a logic low. And when the output is high, it approaches the V plus supply pin, or your positive power supply pin. And when the output is low, it approaches the ground pin, or your V minus pin, or the negative power supply pin if you use dual supply. And the comparator shown on this slide is configured for a non-inverting operation. And so if Vin is greater than your Vref, then the output will go high. And if Vin is less than Vref, then the output will go low. And the comparator can also be used in an inverting configuration. And so in this condition, Vin, your input signal, is instead connected to the inverting input. And Vref, the reference signal, is connected to the non-inverting input. And so because we just simply swapped the inputs, the output behavior can be considered as inverted. And so now if your Vin is greater than Vref, then the output will go low, and vice versa. If Vin is less than Vref, then the output will go high. And we divide comparators into two main types based on the design of their output stage. And these two types are open drain, open collector output, and push-pull output. Open collectors are built with bipolar transistors, and open drains are built with MOSFETs, but generally the naming is pretty interchangeable, and it means the same thing. And pretty much the difference between these two types comes down to whether you need a pull-up resistor or not. And so the one on the left, which is the open drain output, it has an output stage consisting of a single NPN transistor. And so when this transistor is on, it actively sinks current from the collector to emitter, and it pulls that output voltage down very close to ground, or 0 volts. And how close the output can swing to the ground depends on that saturation voltage from the collector to emitter. And when the transistor is off, the collector looks like a high impedance, and it has essentially no effect on the output voltage. So in this case, small amount of current is being sourced from the V plus pull-up voltage through the pull-up resistor, and then your output voltage can rise to a logic high. And so without this pull-up resistor, your output voltage can just float to an unknown state. And so for this type of comparators, you need a pull-up resistor on the output pin. Push-pull comparators, on the other hand, have an output stage that consists of a pair of output transistors. And so either the upper or lower transistor in the pair can turn on and actively source or sink current in order to drive that output high or low. And so in this example, the P channel FET on the top, it sources current to push the output high, and while the N channel lower FET would turn on to sink current to pull the output low. And so because of that, you don't need a bullet resistor for a push-pull comparator. Okay, now I want to go over some use cases of when you might want to use a push-pull or an open drain. On the left, here is an example of where a push-pull might be useful. And because the push-pull can actively both sink and source current, it can quickly drive the MOSFET on and off to charge that and discharge that high gate capacitance. And on the right, you have some examples why you might want to use open drain comparators. The two outputs of a window comparator are like tied together. And so you can do that with open drain's output since all the comparators on the output bus share like the same bullet resistor. And open drain outputs are also good for level shifting, where the comparator supply voltage and the logic voltage is not the same. And all open drain comparators can be pulled up to a voltage that's equal to or lower or also higher than the comparator supply voltage. And so if you have a use case where you might want to level shift down or up, then you might want to use a open drain comparator. And now I kind of want to go over some of the DC parameters or DC specs of the comparator. So first you have your input offset voltage, or VOS, and that's usually represented as a voltage source in series with the non-inverting input. You also have your input bias current, or IB, and that's represented as a current source flowing into or out of the comparator inputs. You also have input common mode voltage range, or VCM, and that's the range of allowable input common mode voltage before your input transistors will start to saturate or cut off. Input differential voltage range, or VDIF, that's the maximum allowable differential voltage across your inputs. You also have voltage output high from the rail, or VOH, and that's essentially the maximum logic high voltage that's relative to your positive power supply voltage. And on the other hand, you have voltage output low from the rail, or VOL, so that's the opposite, and that's the minimum logic low voltage that's relative to your ground pin or your negative power supply pin. You also have output short circuit current, and that's the maximum output current that can be sourced or sunk by your output stage transistors. And quiescent current, IQ, that's the typical current consumption of the device when the output current is 0. And you have power supply voltage range, VS, the range of allowable power supply voltage that is good for your device. And one common definition of common mode range is the common mode voltage is equal to the average of the two input voltages. And this is true for op amps under feedback, where your inputs are often maintained within microvolts of each other through negative feedback. But for comparators, this is not true. The input voltage limit applies to each input individually. And this is because comparators are rarely operated with the inputs close together, and they usually are operated with several volts difference between the inputs. So for example, say you have a comparator valid input voltage range up to 3 volts, so from 0 to 3 volts. If the reference voltage is 2.5 volts and the input signal is 3.5 volts, you might expect that this combination is legal because the average between the two is 3 volts. But again, for comparators, this is not true. The 3.5 volts is violating this input range, because it's outside of that 0 to 3 volts range. And therefore, your output condition may be invalid. And so when you're working with comparators, do not average the comparator input values. You want to look at each input individually and ensure that they're both within the specified input range limits. We do have a technical article coming out soon on E2E, And so if you're interested in learning more about this topic, you should go definitely check it out. It should be up soon within the next couple months. And another common question asked is, what can I do if I expect my input voltage to exceed the supply rails? And this could happen, for example, if you had a negative voltage lower than your lowest supply pin, which might come from switching noises in a DC-DC converter or ground sets or ground shifting in industrial and automotive applications. And so with some exceptions, most low voltage and CMOS devices have ESD protection diodes on all the external pins as shown in this diagram. And these diodes will clamp any overall voltages to the supply rails, and they'll start to conduct at about 500 millivolts past the rails, and then they're in full conduction by 800 millivolts. But these internal ESD diodes are not designed for continuous power dissipation, and the current must be limited to less than the apps max input current specification listed in the data sheet. And we at TI, we recommend limiting the current to 10% or less of the apps max input current, or about 1 milliamps or less for most devices. And the more current you can limit, the better it is, as you can protect your input pins of the comparator. And the current is commonly limited by adding a resistor in series with the input. And a rule of thumb is to add 1 kilo ohm per volt of expected overvoltage. So say you expect to have a 5 volt overvoltage on the input pin, then you put in a 5 kilo ohm resistor. You can also add an external Schottky clamp diode if the event is expected to occur frequently or for long periods of time. So you expect to have a negative voltage for a long period of time, then you could use a Schottky diode. And this is because Schottky diodes have lower forward voltages, and they'll start to conduct before the internal diodes do. And so that helps take off the load off the internal ESD diodes. Just be aware that the outputs may be incorrect if the input common mode range is being violated. And since you're operating outside of that common mode range, we cannot warranty expected behavior, and that doing so will be at your own risk. But this method of current limiting and adding a Schottky diode is just a technique that you can use to prevent damage as well as phase reversal. We have an app note that goes a lot over this stuff in detail, specifically for the LM339 family. And we also have a technical article coming out soon that talks about negative inputs and phase reversal. And so these are great resources to look at if you're ever running into issues with common mode voltages. And next, I want to discuss about the offset voltage. And this is one of the critical DC spec. And since the VOS of a comparator creates an additional DC voltage in series with the non-inverting input, it has a major effect on the threshold at which the output of the comparator changes states. And so let's analyze this circuit with 3 different VOS values to better understand that effect. And in this example, we apply a reference voltage of 2.5 volts to the inverting input. And on the input signal, we have a slow-moving ramp signal transitioning from 2.46 volts to 2.5 volts, as you can see in this dark blue waveform. And the offset voltage adds to the input signal to create a total effective input signal equal to Vin plus VOS. And so if your offset voltage is 0 volts, then the total input voltage is equal to Vin plus 0, and your circuit just works as expected. And so when Vin is greater than 2.5 volts, then Vout will go high. And then when Vin goes back down below 2.5 volts, then Vout will go low, as you can see in this red waveform. What happens if you have an offset voltage of plus 10 millivolts? Then the total input voltage will be equal to Vin plus 10 millivolts. So now the output will transition at a lower voltage of Vin because that added voltage from VOS allows the total input voltage to reach 2.5 volts earlier. And you can see in the orange waveform here that Vout is high when your Vin is greater than 2.49 volts, and then it goes back down low when it goes below 2.49 volts. And then similarly, if your VOS is negative 10 millivolts, then your total input voltage is equal to Vin minus 10. And so now the output will transition at a higher voltage of Vin because that voltage is being subtracted from the negative VOS. And you can see in this light blue waveform here that VO is high when your Vin is greater than 2.51 volts, and then it goes back down low when you go below 2.51. Just keep in mind that not only does the threshold voltage change due to the VOS, but the timing of the output waveform will also be affected. And so, for example, when VOS is plus 10 millivolts, the output waveform is high for approximately 600 milliseconds. And when VOS is negative 10 millivolts, and your output is high for less than about 400 milliseconds. So it's much shorter. And this timing behavior may cause issues in certain designs, but many engineers are used to designing with modern op amps that may be accustomed to offset voltages in the range of microvolts to a few millivolts. But comparators typically have offsets that are somewhat higher, ranging from like 2 millivolts up to 15 millivolts. And so that leads to a common issue in a lot of analog circuits, and that is noise. And the comparator is a circuit with an analog input and a digital output. And so noise will definitely affect the operation of the comparator, whether it's external or internal noise. And here we show a comparator with a voltage divider that applies 2.51 volts to the non-inverting input. And we have an input signal that is a noisy triangle wave applied to the inverting input. And looking at the input and output waveforms, we can observe that the noisy triangle waveform and its associated digital output is shown right here. And the diagram on the right shows the results of the zoomed in portion of this red circle area. And so looking at this waveforms, you can see that the output noise near the 2.5 volts threshold can cause the output to rapidly change state. And this is sometimes referred to as chatter. And this happens because the noise causes the input to rapidly move above and below the threshold. And it will continue to change state back and forth until the input voltage stays above the threshold. And as you might imagine, this chatter caused by input noise is normally an undesirable condition that we would like to eliminate. And this chatter most commonly affects slow-moving inputs such as temperature or battery level monitoring. And so what can we do to alleviate this noise effect? And so sensitivity to noise can be reduced through the application of what we call hysteresis. And hysteresis is a form of positive feedback that creates two distinct threshold levels. And the first threshold is set for when the input is increasing, and the second is set for when the input is decreasing. And in this example, the threshold when increasing is set to 2.7 volts, and the threshold when decreasing is set to 2.3 volts. And this 400 millivolts separation of the threshold sets the amount of hysteresis in the circuit. And the thresholds are set by the values of the resistors in the voltage divider and by the feedback resistor going from the output to the non-inverting input. And this 400 millivolts of separation between your VH and VL creates protection against sudden changes in the output state, since the level of the expected input noise is much smaller than 400 millivolts. And since the comparator is in an inverting configuration, the signal applied to the inverting input goes above, as it goes above 2.7 volts, the output will transition back down to a logic low. And once the input signal is driven below VL, then the output will transition from a logic low to a logic high. And so let's go back to the same circuit that we analyzed previously. now with the 400 millivolts of hysteresis applied. We now have two different thresholds, the lower threshold being 2.3 volts and the upper threshold being 2.7 volts. And notice that when the input waveform is increasing, the output will not transition until the first time the input goes above the threshold voltage of 2.7 volts. And once the input is above 2.7 volts, the output will not transition again until the first time the input goes beneath the lower threshold of 2.3. And so as long as the noise is lower than the hysteresis range of 400 millivolts, then we will not see that chatter that we saw previously. And so that means the amount of hysteresis used is set accordingly to the noise that you expect to see in your system. And some of our comparators at TI have internal or built-in hysteresis into the device, but in general, the amount is normally just a few millivolts, which could be enough if you only expect a small amount of noise in your system. And this list gives some examples of comparators that have this internal hysteresis. Keep in mind that devices with internal hysteresis can still use the external hysteresis circuit that we described in the previous slide if you need more hysteresis than what is internally provided. It would just add on top of the amount of internal hysteresis to the device to create a total amount of hysteresis. And so say if you want 10 millivolts of hysteresis, and say you're using the TOV3601, which has 3, then you just need to design the hysteresis circuit to create 7 millivolts. We also have a lot of resources that go in depth about the effects of noise and chatter in comparator circuits, as well as some circuit cookbooks that go over the step-by-step procedure on how to design the hysteresis circuit for both non-inverting and inverting configuration. And the links to them will be included in this PowerPoint, but of course, they're also published on our web. We also have a hysteresis calculator tool where you can essentially input your desired hysteresis and circuit parameters, and it will automatically give you the resistor values that you need for your voltage divider and feedback resistor, depending on you want a non-inverting or inverting configuration. And this is a great tool to use as like a starting point or as a reference to check your hysteresis math work or circuit. Now I want to go over the AC spec, and the most common one is the propagation delay. And this is the D time required for the output to reach 50% of its final output level when the input changes to 50% of its final input level. And notice that two propagation delays are specified, one for the low to high transition, or TPLH, and the other for high to low transition, TPHL. Besides the propagation delay, we also have the rise and fall time, TR and TF. And this is the time required for the output to transition from 10% to 90% of its final value. And note that the propagation of a delay of a comparator can be different for the rising and falling edge due to the sizing and impedance of those output stage transistors. And something that's commonly misunderstood is the definition of input overdrive. And input overdrive is defined as the additional input signal amplitude relative to your reference level. It's not just the simple change in input amplitude. And as you can see in this example, assuming you have a reference voltage of 0 volts, and your input peak-to-peak voltage moves from -80 to 20 millivolts, then your input overdrive level is equal to 20 millivolts because it's the amount that is additional to that is relative to the reference level. So why is this overdrive value important? And we care about input overdrive because the propagation delay time of a comparator is greatly influenced by the amount of input overdrive. So usually in data sheets, the propagation delay is a specification and the input overdrive is usually a condition for that specification. And overdriving the comparator input results in a much faster propagation delay time. And this reduction is limited, but it can be significant as you step your overdrive from 5 millivolts to 100 millivolts. And the plots on the top of the slide show the change in propagation delay versus overdrive for the high-speed device, our high-speed device TOV3501. And as the left-hand plot shows, the propagation delay time almost doubles from just over 3 nanoseconds to 8 nanoseconds as you step down from your overdrive voltage from 100 to down to 0. And so just be careful when comparing comparator propagation delay specifications. Make sure they're specified at similar overdrive values, and look for the overdrive versus propagation delay plots and as well. And generally, for the fastest response times, the input signals applied to your inputs should be made as large as possible. And the final AC specification that we'll discuss is the maximum toggle frequency, and that's essentially the maximum switching frequency of the comparator. And this specification gives an impression of the overall speed of the comparator and how fast the comparator can detect a signal going from low to high. And now I kind of want to talk about a common issue encountered in comparator circuits, and this is known as startup output state uncertainty. And startup state uncertainty means that as the comparator's power supply is being ramped, the output may transition back and forth between states regardless of what you have on your input pins. And that means the output may provide a false or incorrect state during the startup until the supply voltage reaches that minimum supply voltage of the device. And this could be an issue if a circuit following the comparator comes to life quicker during the startup and it acts upon this unintended output state coming from the comparator. And having a known output state is useful for understanding startup conditions, because startup conditions of the comparator may impact that downstream signal chain. And this behavior can be illustrated in the circuit shown here using the TOV3492. And in this example, the supply voltage is being slowly ramped up. And we have two different sets of input conditions shown here in the red and the black. And so for the first case, shown in the red, the voltage on the non-inverting input is greater than the voltage on the inverting input. And so that means your output should be a logic high. And we see that as the supply voltage ramps from 0 to 3 volts, the output actually flips state from a logic low to a logic high, and then back down to a logic low before stabilizing at a logic high once the supply reaches that minimum supply voltage. For the second case, shown in the black, the inverting input voltage is higher than the non-inverting input voltage. And in this case, the expected output should be a logic low. But we see that the output briefly transitions to a logic high as the supply voltage ramps up. And this uncertain startup behavior is not unusual, and you can see it in a lot of comparators. But thankfully, some of our newer and more modern comparators have internal circuitry that addresses this issue. And it addresses this issue by having an integrated power on reset circuit, or POR. And what POR does, it controls the output when a supply is ramping up or down. And when the supply voltage is greater than or equal to the minimum recommended operating voltage, then the output will reflect the state of the inputs. And for a push-pull, the comparator output will be held low during the startup. And for an open drain, the output will be held high Z or high impedance during the startup. Just make sure to remember to check the datasheet to see the comparator specific behavior. And if we repeat the supply ramp test from the previous slide, we can observe that the comparator output will be held low here until that minimum VCC of 1.2 volts is reached, and then the correct output state will be maintained. And this is an important feature in a lot of certain applications where reliable startup behavior is critical. We also have several different devices with integrated features and functions to help with board space issues. We have a comparator and amplifier combination, comparators with integrated reference, so you don't need to design a reference level with extra resistors. It's just integrated into the device. We also have differential outputs as well, and level shifting devices, and LVDS as well on our higher speed devices. So now I kind of just want to go over a couple devices that has these features. Here we have the TOV 4062 and 4082, which is our lower powered dual comparator with an integrated reference connected to each comparator. And integrated reference are nice because it reduces that need to create that reference on one of your inputs, therefore reducing the amount of resistors and board space. And this reference has a high voltage or high threshold accuracy of 1% over temperature with a 60 millivolt internal hysteresis. And because of this, this makes the TOV 4062 and 4082 well suited for applications such as monitoring two different thresholds of a battery. Like one threshold could be for like a warning level, and a second threshold could be for shutting down and turning off the device if it reaches like a certain level. Here we have the TOV 3604 and 5, which is one of our newer LVDS comparator with only an 800 picosecond pop delay and a 1.5 gigahertz toggle frequency. And so this device is really high speed. And low voltage differential signaling, it allows for increased data throughput and it optimizes power consumption. And it's really designed to drive and interface directly with downstream devices such as high-speed FPGAs and CPUs. And so LVDS makes the TOV 3604 and 5 really well suited for LiDAR and time-of-flight applications, as well as for test and measurement systems. And with such a large selection of comparators, how do we find the correct device? And we have several different ways. Of course, you can use TI.com and use our comparators web portal. We have our cell guide selection software as well. And of course, you can ask us on the E2E support forum and ask us recommendations on what device you would like.